Hi everyone, I'm Allison, and congratulations that you have all made it to Lab 7. In this lab, we explore policy-based reinforcement learning methods, especially A2C and PPO, and we focus on both low-dimensional and high-dimensional continuous control tasks. This is what we'll be covering today. The background on policy-based RL, which is A2C and PPO, and generative advantage estimation, and the description of the environment, which is Pendulum and Walker 2D, the implementation and the tasks that you need to complete, and fourth of all, the grading and submission policies. Let's spend a bit more time on the environments themselves. Okay, let's go through the background really quickly. The A2C is the simple advantage and actor-critic algorithm. The actor represents a policy network, which is what you will do or what probability of a certain action under a certain state. And the critic is the value function, which is estimating the state. And the advantage is how you quantify how much better an action is compared to the average. This method enables more stable updates and support learning in continuous action environments like Pendulum. And this is the pseudocode that you may need to follow. PPO introduces a more stable update mechanism than the vanilla policy gradient and swerved the limitation of using the second-order derivatives in trust region policy optimization. The clipping objective restricts how much the policy can change at each step, which prevents sudden large destructive updates. The total loss consists of the actor loss with clipping surrogate objective, the critic loss, and the entropy bonus to encourage exploration. And PPO is known for balancing performances and stability, especially in high-dimensional tasks. In this lab, first let us introduce the pendulum environment. The pendulum environment is a classic control problem. The system consists of a pendulum attached at one end to a fixed point and the other being free. The pendulum starts in a random position, and the goal is to apply torque to the free end to swing it into an upright position, which is its center of gravity right above the fixed point. And the observation state includes the xy position, which is calculated by cosine and sine of the endpoint, and which is the free end, and the omega, which is the angular velocity. And what you can do is by applying a torque, which is in the range of -2 to +2. And the reward is calculated by the following formula, which encourages minimal angle deviation and low torque use. This is a low-dimensional environment, making it a good starting point to test A2C and PPO. Now let's get to the harder environment. Walker 2D is a much more complicated environment in the Majorco suit, and the goal is to make a two-leg robot, as depicted in the figure, walk forward or walk to the right. And the observation space consists of a vector of 17 continuous features representing body positions, velocities, and joint angles. And the action space is 6 continuous joint torques as shown in the picture. You can find more information about the observation in the link below. And the reward consists of 3 parts. The first one is the forward movement. When your walker walks forward, it gets a reward. And the second one is a healthy reward to prevent the reward from being too sparse. So as long as your walker is still alive, then you get a reward of value 1. And the third one, the control cost, is to penalize sudden large updates or sudden large movements. Training on these environments poses multiple challenges, such as high-dimensional state and action spaces, and balancing between locomotion, stability, and efficiency. So, for task 1, you need to implement A2C on pendulum, and task 2 is PPO on pendulum to make sure that your implementation is correct. And the third one is to use your PPO on Walker 2D. And now let's get to the grading policy. And you need to hand in a report, and with an introduction of 5 points. Please provide a high-dimensional introduction to your report, and it's better if you can include a table of contents. And you need to describe in detail of your implementation, how you obtain stochastic policy gradient and TD error for A2C, how you implement the clipping objective in PPO, how you obtain the estimator of GAE, and how you collect samples from the environment, how you enforce exploration, and explain how you use weight and bias to track your performance and plot the loss values. And the more important part is the analysis and discussions. Please plot the training curves and compare the 3 tasks. And you need to compare the sample efficiency and training stability of A2C and PPO. And please perform an empirical study on the key parameters, such as clipping parameters and entropy coefficients. And some additional analysis will give you some bonus points, up to 10 points. And also, as in Lab 5, you need to hand in a demo video, which is about 5 to 6 points. We prefer that you deliver the video in English, and you need to explain how you implement your code and the model performance, which is demonstrating your obtained models with a video. And you will also need to provide model snapshots. Please be noticed that model snapshots will not be graded if no valid demo video is provided. And here is the grading policy for the model snapshots. For task 1 and task 2, we apply a linear scoring percentage as shown in the formula. And for task 3, in order to test your sample efficiency, we will provide the grading policy as shown in the table, which by everything that we mean is that the more efficient your agent is, the higher points that you get. And the submission policy is similar to Lab 5, and you need to hand in those checkpoints and your report, your video, and all of your source code. And please directly zip all of them without putting them into a folder first. And this is all for today. Thank you all for your attention, and good luck.